Okay. Hello, everybody. My name is Dan Wise. I'm a software specialist for the CDH team at NEUdose, and this is our presentation. So what is CDH? It stands for Command and Data Handling. It's essentially the brain of the satellite, and it controls how commands are processed, information flow, storing data, collecting and processing telemetry data, and a whole lot more. All the work we do is embedded software and hardware, so working with microcontrollers and developing programs in C and C++. Our team is pretty diverse, but mostly comprised of mechatronics and computer engineering students. Our team lead, Paula, is in ISci, and you can talk to her later at the expo. Moving on, our key objectives as a team are to monitor the health of each satellite subsystem, change subsystem state to ensure nominal satellite operation, store scientific data, create scientific data packets for downlink, and execute commands received from ground station. So essentially communicating with all the other subsystems and modules and bringing it all together, making sure everything does what it's supposed to do at the right time and get the right data. The components of the CDH system are as follows. We have the onboard computer, the CDH motherboard or interface board, a secondary onboard computer, and the flight software, which I'm going to go into detail about all of these in the following slides. You can see on the right, that's an image of the bus stack. So that's housed just under the payload, and that's where all our boards are. So hardware. The OBC is the primary computer of the CDH system. We purchased it prefabricated from GomSpace and chose the Nanomind A3200. It's got pretty much everything we need, a real-time clock, more than enough memory, good power, usage, stats. However, the one problem was that it wouldn't interface with the rest of the satellite. We couldn't connect our other devices to it. So we created the interface board. Now this is a custom in-house design, and it connects the OBC to the rest of the satellite. It provides PC104 interface to comms and EPS and has an extra connector for payload. And you can see in the image on the right, that black box in the middle there is the OBC mounted on top of the interface board. The SOBC is another custom in-house design. It was originally intended to be used as the OBC. However, it was changed because the SOBC would be untested in space and therefore potentially unreliable. Now it's a secondary payload or a secondary onboard computer. That's what the S in SOBC stands for. And it works pretty much the same as the OBC. However, it won't risk the success of the primary payload. So at some point during the mission's lifetime, we're going to turn on the SOBC, let it run, make sure that it's working the same as we expect the OBC to. And now we have a bunch more data of how we built a computer that works in space. So that's an extra little cherry on top for NEUdose. Moving on to software. We have two primary components of the software. That's the real-time operating system, FreeRTOS. It's the same one that comms is using. And we chose it because it's lightweight, versatile, and it already works on the OBC and SOBC boards. On top of that, we're going to run NASA's core flight system as our flight software. It has many layers of abstraction, allowing for parallel software development. It offers a lot of commonly used applications that we don't have to write ourselves. And it's written in C, which is good for our mechatronics and computer engineers. One major undertaking of the CDH team is the CFS to FreeRTOS port. The goal is to get our flight software, CFS, to work on FreeRTOS, because currently it's only made to work for Linux, RTEMS, and VxWorks, I believe. But we're not using those operating systems, so we have to write an OS abstraction layer to make that work. And porting it is going to be a 4-stage process. First, we've already stubbed out all the code, so that means we took the Linux abstraction layer and erased everything that called Linux functions. And now we're moving on to rebuilding it and putting FreeRTOS calls in the place of those. So hopefully soon we can get that working, test it, and revise it until it's complete. The layers of the software for the CDH system are as follows. I know I said there was 2 main components earlier, but it's a little bit more complicated than that. On top, we have the mission application layer where we run CFS applications. So that's the main part of CFS that we're using. Under that, the abstraction layer that I just talked about, that's the one that puts CFS on FreeRTOS, as well as CSP, which is the communication protocol we're using to communicate with other subsystems and with the ground station. FreeRTOS we just mentioned, and underneath that, a hardware layer of bootloaders, board support packages, and device drivers. And those all are the first link to interfacing with the hardware, the OBC, interface board, and SOBC that I talked about earlier. So now more about the mission application layer. This is a diagram of what our mission application software actually looks like, kind of. In purple, we have mission developed applications for interfacing with different subsystems. So one for comms, payload, and EPS. And each of those are going to handle the logic pertaining to each of those subsystems. And if we get a command to say, get payload telemetry data, then that's going to go through the payload app so that it knows what's happening. In green, we have CFE core apps. So these are really the basics of how CFS works. And those are essential to every satellite. They include them on everything. And that includes stuff like event services for error messaging, executive services for app management, the software bus for messaging between apps, and more. Excuse me. And in blue, CFS apps are other applications that might not be used in every satellite, but are still pre-made by NASA, and we're going to be using them for various applications. Now, when I say mission application, it can get a little confusing because you're thinking, well, is this like an iPhone app? What does this look like? So this is an example of the code that we work with. When I say mission application, this is really all I'm talking about. It's C code. It's hundreds of different files and header files that are kind of like this. And yeah, that's just an example. That's the main loop of the scheduler app. So the satellite operation is, this is basically just explaining the flow of what's going to happen on the satellite. So once we launch and get into space, we have a 30-minute timer to let the battery charge up, followed by initialization. That's where the CDH system is going to turn on, comms is going to turn on, of course EPS is going to turn on before all of that. And then we beacon down to the ground station, establish a connection with the ground station, and downlink some initial telemetry data. After that, we're in active mission mode where we're going to power on the payload and begin collecting that data. And when it's ready, we beacon again, form that connection, and downlink the data. And hopefully, we can get some successful scientific research done from that. And below, these tiered low power modes are just showing what subsystems are off depending on how much charge we have. So in the worst case scenario, off mode, we have everything off. Then EPS would power on, then CDH, then comms, and finally payload, although it's not shown that it goes on. The communication architecture for CDH is three-pronged, I would say. We have the software bus, which is a virtual bus within CFS for intra-system communications. So that's all within CFS, or within the CDH system. We have the CAN bus, which was mentioned earlier, I believe. That's for communicating with other subsystems. So you can see at the bottom of this diagram, it goes between EPS, comms, payload, and CDH. And libcsp is the protocol we use for packaging message onto the CAN bus. So in these middle sections here, we have apps that are going to put that libcsp protocol on the messages, put the headers on so that they can be read by other subsystems. That's all for the software. Now a little bit about testing. For hardware, we have an Atmel STK600 development board because the OBC we bought is very expensive and we don't want to do development on that for fear of breaking it. So we have the STK600 that allows for a safer environment for testing and developing. And it works essentially the same as the OBC, but it's not ready for space. It doesn't have the radiation proofing that the OBC does. For software testing, CFS includes a big unit testing library for validating software. And we're going to be measuring CPU load margin to determine the performance of our software. And obviously, we're going to try to optimize that as best we can. And that's something we have to work on in the future. And of course, we use GitHub for version control to make sure that we always have a version that builds and that works. And yeah, that's software testing. Our timeline for CDH, this is a little bit outdated, but you can see we have a lot of stuff going on in parallel. In blue, that's the stubbing of the porting from CFS to FreeRTOS. In orange, that's high-level logic, so writing those mission applications. In blue, CSP communication and developing that and making sure that works properly. The ground station capability in red, hardware testing in green, and finally the interface board testing and fabrication in purple. So hopefully we can get all those done at once. It's a lot on our plate, but our main next steps are to test the OBC, to fabricate and test the interface board and SOBC, to fly the prototype motherboard on the SPX weather balloon mission. And for software, really need to port CFS to FreeRTOS. That's our biggest priority. And then we need to test CAN and CSP communication and finalize the CFS data path and mission application code. So thank you. And if you have any questions, please visit the CDH booth in the expo where me and Paula will be there to answer your questions.